Now we have learned a bunch of different tests. And so what I did was, I was just like, this is kind of hard to organize, right? We've learned all these tests. When do I apply what? What are the conditions for what? And so that's what the first worksheet that goes with this video is a table that I made just for myself to organize it. And I thought this might help you guys too. So if we look at it, here's the deal. If we go through these, the first test is the divergence test. And so what does it determine? So all of these tests are not for convergence and divergence. Some are for both or one or the other. So the divergent test, it only tests to see if a series is divergent. It doesn't tell you anything about convergence. So if we know it's divergent, we know it isn't convergent. But if it fails the divergent test, we can say nothing, right? We just don't know. So the conditions to apply this test is there's no conditions. You can apply it to any series. So basically, you take the limit as n goes to infinity. If it doesn't equal to 0, then it's a divergent series right off the bat. If it does equal to 0, we just don't know. And so we're going to try all these other tests to see if maybe it converges. So that's what you got to do with that. The integral test. This is a test that will test for convergence or divergence, and it can be applied only to a series that's positive and decreasing and continuous. So that's when you take the integral from 1 to infinity of the function version of the series and see if you get a limit. If you get a limit, if it converges to a limit, then the series is convergent. If it diverges, then the series is divergent. So it's got to meet these conditions, and you can tell from this test whether it's going to converge or diverge. The comparison test is when you take a series you don't know what's going to happen with it and you compare it to a series you do know what's going to happen. So maybe you compare it to a series that you know converges. If you're comparing it to a series that you know converges, then the series you're testing has to be less than or equal to every single term of the known series. If that's true, then the series you're testing that you don't know about, it's also convergent. Or you take a series that you know about and you know it diverges. And as long as the series that you're testing is greater than or equal to every term of the series that you know that diverges, you can say that the series you don't know about also diverges. Then we have the limit comparison test. If you have a known series, B sub n, and you take the limit of the unknown series, and of the unknown, that you take the ratio of the unknown over the known, and it gets to the limit exists, some value c. If c is positive, then either both of the series converge or they both diverge. So if the known series converges, then they both, and you get this limit value, then they both converge. If the known series diverges and you take the limit of the ratio and you get some value c that's greater than 0, then they both diverge. That's how the limit comparison test works. Then we said, what do you do about alternating series? Okay, you can take an alternating series, and if you can show two things, that it's a decreasing series and that the limit as n goes to infinity of the series without the plus or minus part goes to 0, then you can say the alternating series converges. So that one only tests for convergence. Absolute convergence test says if the absolute value of all the terms converges, then that series also converges. That only tests for convergence. You can apply the absolute convergence test to any series. The ratio test. This will test for convergence or divergence, but remember, it can also be inconclusive, right? If you take the limit and you get a 1, then it's inconclusive, and that's the same thing for the root test. So let's go on to the next sheet, which is where we just try to strategize about some of these things. So let me find where I put it. I'm gonna need that for sure. Okay, hang on. Let me find it. Okay, hang on. Let me just maybe pause this. Is that it? No. Is that it? No. Is that it? All right. I'll be right back. Okay, found it. Now, so if we're going to do some, here's a couple of series we know along the way. Geometric series. So the geometric series is a known series. We know all about it. If we have a times r to the n, this is the form of a geometric series. If the absolute value of r is less than 1, then it will converge. If the absolute value of r is greater than or equal to 1, then it will diverge. So this, we know about geometric series, which is helpful because if we know about it, then we can compare. If we know a series diverges, we can compare something to it. If we know a series converges, we can compare something to it. So geometric series are known. Also, we know about the p series, right? 1 over n to the p, or x to the p, we'd say. If we're summing this from n is 1 to infinity, if p is greater than 1, it converges. If p is less than or equal to 1, it diverges in this case. So this is the p series that we know about. Let me make sure I didn't make a mistake when I was writing that down. All right, cool. That's it. So strategy. What can we do? All right. Well, I've got a few bullet points here. So let's just talk through these real quick. If a series has a form similar to a p series or a geometric series, we could try using a comparison test or the limit comparison test. That's a good idea because we know about one of these. If you look at it and you can just spot that if you took the limit of a sub n and it would not equal to 0, then it's divergent. There's no question it's divergent. So that's the divergence test. We can always apply that. But if you get 0, then you can't automatically say it's convergent. You got to try something else. If the series is alternating, try the alternating series test. Although we did a couple of alternating series that it would be hard to just do the alternating series test. We had to apply an absolute, look at an absolute convergence like the ratio and root test. Sometimes we use that as well. If the series has a factorial or a base raised to the nth power, try the ratio test. If you have something to the nth power, try the root test. And if you can easily, if you can model the series off of the function f of x, and it's decreasing and continuous and positive, then you can easily integrate it, then use the integral test to test for convergence or divergence. So let's just look. We've got 6 examples. So number 1 is this. And so I'm just going to talk about what would be a good strategy to use here. Okay. This, the series n is 1 to infinity of n minus 1 over 2n minus 1. This is a sub n. I'm just looking at that. And if I take the limit as n goes to infinity, the limit as n goes to infinity of n minus 1 over 2n minus 1, I've done enough of these to know it would be 1/2. But if I didn't spot that right off and I wanted to use L'Hopital's rule because it's infinity over infinity, you could take the limit as n goes to infinity of the derivative of the numerator, which is going to be 1 minus 0, over the derivative of the denominator, which is going to be 2 minus 0, and you'll see the limit is 1/2, which did not equal to 0, so this guy is divergent. That's the divergent test. Number 2, what would I do with number 2? I've got the sum from n is 1 to infinity of the cube root of n cubed plus 1 all over 3n squared plus 4n squared plus 2. I would look at the leading coefficients of the ratio. And this looks a little bit like, the cube root of n cubed would be like n, maybe. And over, this is cubed, I wrote that down, over 3n cubed, over 3n cubed. So I would probably do a comparison test of 1 over 3n squared. Because this is a p series where p is greater than 1. So this guy converges, and I would test a few terms to just satisfy myself that this is less than this one, and I would do a comparison test. That's the route I would go for number 2, and I would think that I could show that this was, I would try to show that this was convergent based on that test. Number 3, we have the sum n is 1 to infinity of n e to the negative n squared. All right. what would I do with this guy? I naturally rewrote it like this. N over e to the n squared. Okay. There's two directions you could probably go here. This one, I said I tried the ratio test. I would try the ratio test and see if I got a limit to exist and see if it's greater than 1 or less than 1. And if it concludes one way or the other, then I know it's convergent or divergent. Or I would try the integral test where I said, let's consider f of x is x over e to the x squared. I would try to show that this was, it is positive, continuous. I would show that it was decreasing and apply the integral test. So you could go either way with that, integral or ratio. Number 4 is this one. N is 1 to infinity of negative 1 to the n cubed over n to the 4th plus 1. This one is alternating series, right? I would try the alternating series test here, and then where you take the absolute value and then take the limit of, this has to be positive and decreasing, and take the limit of this. I would try the alternating series test here. Number 5, what is this one? Okay. The sum from n is 1 to infinity of 2 to the n over n factorial. Okay, this one is just screaming to me ratio test because of the factorial and because of the 2 to the n. I would use the ratio test here. And number 6, what would I do with this? 6 is the sum from 1 to infinity of 1 over 2 plus 3 to the n. This one, I would, see that 3 to the n? This looks a lot like the geometric series 1/3 to the n. 1 over 3 to the n. And this is known to converge, and I would probably do a comparison test here. So that's an idea of how you could decide which test to use with. All right, that is our strategy for testing series.